We tend to think of democracy as a battle of ideas, right? A clash of values. But what if, underneath it all, it's actually a battle of math? Today, we're going to pull back the curtain on the hidden algorithms that decide our elections. And you're going to see how the answers they spit out aren't always as fair as they look. All right, let's get into it.
Look, we're all raised on this core belief. Every single vote matters. It's supposed to be the bedrock of a fair society. But what if the systems themselves, the actual math we use to tally those votes, are kind of broken? What if they can produce wildly different, even totally contradictory results from the exact same set of votes? Well, that's the big, thorny question we're tackling today.
So it all starts with this beautiful, simple idea. One person, one vote. I mean, that sounds like the very definition of fairness. And you know what? When you've only got two choices on the ballot, it really is that simple.
Yeah, when it's candidate A versus candidate B, no problem. The one with more votes wins, end of story. But what happens when you toss in candidate C, or candidate D, or E? All of a sudden, that simple math gets incredibly messy, and the whole idea of what it means to be the winner becomes, well, surprisingly slippery.
And this is where the real puzzle begins. See, picking just one winner from a whole field of options isn't just a political headache, it's a serious mathematical problem, and it has some truly mind-bending answers.
To really get what I mean, let's forget about politics for a second and step into a classroom. A geology class needs to pick one of three amazing spots for a field trip. This isn't about left or right, it's literally just about rocks. But the voting math, it's exactly the same.
Okay, so take a look at how these votes are structured. The students don't just pick their favorite, they rank all three options, first choice, second choice, and third. So we have all the data. We know exactly what every single student wants. But the big question is, how do you actually count this to find a single, fair winner?
Well, let's start with the method we all know from school elections, the plurality method. Whoever gets the most first-place votes wins. Easy, right? Well, watch what happens. Grand Canyon gets 13 first-place votes, and Death Valley gets 13 first-place votes too. So right out of the gate, the simplest, most common system fails. It's a dead tie.
So, what now? A coin flip? A do-over? But what if the problem isn't the votes themselves? What if it's the method we're using? Let's keep the exact same preferences from the students, but just swap out the mathematical rules we use to count them.
Let's try something called the Condorcet method. Now this one's cool. It basically simulates a bunch of one-on-one matchups. So we ask, if it was just Grand Canyon versus Bryce Canyon, who would win based on the rankings? Then Grand Canyon versus Death Valley. If one option can beat every other option in a head-to-head fight, it's the winner. And when we do that, Grand Canyon wins. No tie.
Okay, let's try one more. This is the board account. Here, we give out points for ranks. Like, maybe a first-place vote is worth 2 points, second place gets 1 point, and third place gets 0. You just add up all the points. And when we run the numbers this way, hey, Grand Canyon wins again. But this leads us to the most important point of this whole thing. The method is the result. Seriously, let that sink in for a second. The votes didn't change at all. The students' preferences stayed exactly the same. All we did was change the math, and by doing that, you can literally change the winner. Now just imagine the implications of that when you scale it up from a classroom to an entire country.
Now, if picking just one winner is that tricky, what happens when you're trying to represent millions of people? We're about to see how this same problem gets way more complicated.
We're talking about something called apportionment. That's the whole process of figuring out how many representatives each state gets in a legislature, like the U.S. House. You have to take all this messy population data and turn it into a nice, clean number of seats. And you can't have half a representative, right? So you have to round. And how you round? Well, that's where the fight really starts. And believe me, this is not a new fight. This debate goes all the way back to the founding of the United States. You had these absolute giants, Alexander Hamilton and Thomas Jefferson, arguing like crazy over math formulas, because they absolutely knew, that the choice of formula could shift the balance of power in the new nation.
So, Hamilton came up with a method that seems like total common sense. First, you figure out the ideal number of seats for a state, which is usually a decimal. Then, you just give each state the whole number part of that. And with the leftover seats, you just hand them out, one by one, to the states that had the biggest leftover decimal parts. Seems totally fair, right? But Jefferson said, not so fast. He came up with a totally different method using divisors. And here's the political genius of it. They both understood the hidden bias in the math. It turned out that Hamilton's common sense method actually tended to give a slight edge to bigger states. In Jefferson's method, it tended to favor the smaller ones. The math wasn't neutral at all. It was deeply political.
But here's where it gets really weird. The rabbit hole goes so much deeper. It turns out that these systems, even the ones designed by brilliant minds, can sometimes just break in ways that defy all logic.
You expect math to be rational. You expect it to be predictable. But when you apply these perfectly logical formulas to the messy reality of democracy, you start getting paradoxes. You get situations where the results are so completely backward, they just feel plain wrong.
Take the Alabama paradox, for example. It was discovered when people were using Hamilton's method. Now, imagine the country decides to make the legislature bigger, to add more seats so there's more representation for everybody. Logically, every state should either keep the same number of seats or gain one, right? But with this paradox, a state can actually lose a seat. It's crazy.
Just look at this simple example. With 100 total seats, State C gets 10 of them. But when we increase the total size of the pie to 101 seats, State C's share suddenly drops to 9. More for everybody somehow means less for them. It makes absolutely no logical sense, but it is 100% mathematically possible.
And these aren't just weird little flukes. It turns out this problem is fundamental. In the 20th century, an economist named Kenneth Arrow proved something absolutely stunning with his impossibility theorem. He laid out a few basic, common-sense rules for what makes a voting system fair. You know, stuff like, if every single voter prefers candidate A over B, then B shouldn't win. And his conclusion? It is mathematically impossible to invent a ranked voting system for 3 or more options that doesn't break at least one of those basic rules of fairness.
And that, right there, is the ultimate takeaway. The hunt for a single, perfect, mathematically flawless voting system. It isn't a political failure. It is a mathematical impossibility.
So if the math is fundamentally broken, if a perfect system is literally impossible to create, where in the world does that leave us? Well, this is the point where we have to move beyond pure math and start talking about human values.
So here's the real lesson from all this. There's no such thing as a perfect system. Every single voting method involves a trade-off. It's a choice about what kind of unfairness you're willing to live with. Math doesn't actually give us the answer. What it does is it holds up a mirror, and it reveals the trade-offs and the hidden biases we have to confront. It forces us to ask a much deeper question, not a mathematical one, but a philosophical one. What kind of fairness do we as a society value the most? And that, ultimately, is the real work of democracy. If a perfect system is off the table, then our job is to understand the flaws in the systems we have, and to constantly argue, debate, and refine them. Because the goal isn't to achieve some kind of mathematical perfection. That's a fantasy. The real goal is to build the best, the fairest, the most representative society we can, using the imperfect tools we have.